The captivating story of our universe, dating back approximately 14 billion years, is undergoing a seismic reevaluation, courtesy of the James Webb Telescope's groundbreaking revelations. Ever since it opened its giant infrared eye on the cosmos after its December 2021 launch, James Webb has pushed the limit of what we can see. Far exceeded all expectations, the time machine has been finding an overabundance of bright galaxies that stretch back to the very early universe. Their brightness, a proxy for their number of stars and hence their mass, is deeply puzzling because galaxies shouldn't have had enough time to become so bulky in such early cosmic epochs. Imagine visiting a foreign land and finding that many of the toddlers there weigh as much as teenagers. You might have questions too. Are the children so large because of something in the water? Or might it instead be that your grasp of human growth is fundamentally flawed? Theorists who pondered James Webb's big, bright, early galaxies felt much the same. Was something fundamental amiss in our understanding of cosmology? Namely, is the age of the universe misjudged, or did the very concept of its origin demands a radical rethink? As scientists grapple with claims that the Big Bang and possibly even general relativity had been disproven, James Webb seems to be trying to add fuel to the fire. Its new observations are now entering the first 500 million years after the Big Bang, when the universe was less than 5% of its current age. For humans, this time would place the universe firmly in the toddler stage. But the galaxies we are observing are certainly not infantile, with new observations revealing galaxies more massive and mature than previously expected for such early times, helping to rewrite our understanding of galaxy formation and evolution. Join us as we dig deep into how James Webb's new discoveries just pushed the boundaries of our cosmic comprehension. Astronomers have long thought they understood how galaxies evolved. First, relatively small clusters of stars formed. These clusters then gathered together to produce baby galaxies. The baby galaxies then coalesced into the giant galaxies we see today. This process, from the first stars to near-mature galaxies, was expected to take about 1 billion years. Because our universe is about 14 billion years old, we needed a facility that could peer back in time and gather the data necessary to validate this theory. That's where the James Webb Space Telescope came in. James Webb Space Telescope is such an enigma that falls in the twilight zone where science fiction and reality meet. Without traveling so much as even a fraction of a second back in time, the $10 billion instrument is going to look at galactic events that happened millions of years ago. As fictitious as it may sound, it works on a very well-known principle. As we know, the speed of light and other electromagnetic waves is about 300,000 meters per second. Over a few thousand kilometers, such as those on Earth, it doesn't usually take light more than a microsecond to travel from one point to another. But in the vastness of the universe, where distances are colossal, light could even take years to travel. For instance, let's say you were observing a star in the night sky. Billions of miles away from its origin, at the surface of this star, light begins to travel and takes, say, 5 years to reach your eyes on Earth. Now, if this star were to die, its light would take 5 years to finally stop reaching you. In short, the farther away the object is, the more time light takes to travel, and the further back in its past we can see. The Webb telescope uses exactly this principle. It is equipped to be sensitive to particularly the longer wavelengths of light that have the capacity of traveling greater distances with minimal waning of brightness. So, to look at the farthest objects in the cosmic void, we must gather these wavelengths of light. In the electromagnetic spectrum, these are called the infrared rays and are associated with heat. It is here where the mind-bending design and build of the telescope comes into the picture. With its infrared eyes and its position far away in space, it's truly revealing the universe as we've only dreamed of seeing it, rife with tremendous advances and surprises. An enormous old galaxy. And most recently, James Webb has made unprecedentedly detailed observations of one of the earliest known galaxies, dubbed GZ9P3. Its name comes from the James Webb Space Telescope International Glass Collaboration and the fact the galaxy is at a redshift of Z equals 9.3, where redshift is one way to describe the distance to an object, hence G and Z 9P3. Just a couple of years ago, GZ9P3 appeared as a single point of light through the Hubble Space Telescope. But by using the James Webb Space Telescope, we could observe this object as it was 510 million years after the Big Bang, around 13 billion years ago. What's more, the team discovered that, much like other early galaxies seen by James Webb, GZ9P3 is far more massive and mature than expected for a galaxy in the infant universe. During the ancient time period in which it's been spotted, it already appears to contain several billion stars. When it comes to the cosmic conundrum of how early galaxies grew to become so massive so quickly, GZ9P3 could be a real puzzle. Not only is it more massive than expected, but it is around 10 times more massive than other galaxies James Webb has seen in similar eras of the universe's history. As Kit Boyette, team member and a scientist at the University of Melbourne, wrote for the Institute's Pursuit publication, just a couple of years ago, GZ9P3 appeared as a single point of light through the Hubble Space Telescope. But by using the James Webb Space Telescope, we could observe this object as it was 510 million years after the Big Bang, around 13 billion years ago. GZ9P3 is simply remarkable. Besides its size and maturity, its shape also reveals clues to its creation. Using James Webb and direct imaging, the team was able to determine that GZ9P3 has a complex shape with two bright patches that reveal its two dense nuclei. That indicates GZ9P3 was likely created when two early galaxies smashed together in the infant universe. This collision may have still been ongoing during the time at which astronomers noticed GZ9P3 with the Webb telescope. As Boyette explained, the James Webb imaging of the galaxy shows a morphology typically associated with two interacting galaxies, and the merger hasn't finished because we still see two components. When two massive objects join like this, they effectively throw away some of the matter in the process. So, this discarded matter suggests what we observed is one of the most distant mergers ever seen. In addition to determining the age, mass, and shape of this ancient galaxy, Boyette and colleagues were able to probe deeper within GZ9P3 to examine the stellar population of these colliding galaxies. Because young stars are brighter than their older counterparts, they usually dominate galaxy images, especially those that are so distant their light has been traveling to Earth for billions of years. For example, a young bright population sparked by the galaxy merger, less than a few million years old, outshines an older population already over 100 million years old. The glass collaboration worked around this by taking spectroscopic observations of GZ9P3, as well as by tapping into direct imaging. Spectroscopy can be used to determine the elements that make up stars. Because young and old stars have different compositions, this allowed the researchers to separate the two categories in this early galaxy. Older stars have worked their way through the hydrogen supply in their cores, having already fused it all into helium, and then fusing this helium to create even heavier elements, which astronomers call metals. This means older stars are richer in metals than younger stars, which are still dominated by hydrogen and some helium. The study team used James Webb to detect specific elements in the older star population of GZ9P3. These target elements included silicon, carbon, and iron, the latter of which is the heaviest element that can be synthesized by stars. This means these stars, when they died in supernova explosions, would have enriched the early universe with metals. Much of this metal content would have gone on to become the building blocks of the next generation of stars. In addition, the team discovered that the population of old stars in GZ9P3 was much larger than previously suspected. This means that, while astronomers have been aware of this cycle of stellar life and death and the increasing metal enrichment of subsequent generations of stars, the GZ9P3 observations indicate galaxies may have become chemically mature faster than had been suspected previously. These observations provide evidence of a rapid, efficient buildup of stars and metals in the immediate aftermath of the Big Bang, tied to ongoing galaxy mergers, demonstrating that massive galaxies with several billion stars existed earlier than expected. Galaxies that sit isolated from their galactic counterparts do form stars, but the process is slow and ends when that galaxy exhausts its reservoir of gas and dust, the materials that form stars. For galaxies close to each other, the process of star formation can be sped up and even revived after it has drawn to a halt. That's because when these galaxies are drawn together by a mutual gravitational attraction, they collide. The merger then causes an inflow of fresh gas that kickstarts a period of rapid starbirth called a starburst, meaning mergers provide an excellent way for galaxies to rapidly grow their stellar populations. Most large galaxies in the universe have grown this way. Our own galaxy, the Milky Way, shows a history of mergers itself. For instance, it has been involved in the cannibalization of smaller satellite galaxies that once orbited it. The Milky Way currently forms stars at a stunted rate, but this will change when it collides with our neighboring galaxy, Andromeda, in around 4.5 billion years. This will cause an influx of gas that kicks off a fresh bout of starburst. Thanks to observations of GZ9P3, astronomers are getting the message that this channel for rapid mass accumulation and star birth was a bigger factor in the early universe than predicted. As Boyette explained, these observations of GZ9P3 show that galaxies were able to accumulate mass quickly in the early universe through mergers, with star formation efficiencies higher than we expected. This and other observations using the James Webb Space Telescope are causing astrophysicists to adjust their modeling of the early years of the universe. Our cosmology isn't necessarily wrong, but our understanding of how quickly galaxies formed probably is, because they are more massive than we ever believed could be possible. A collection of ancient galaxies transformed the entire universe. But while James Webb has created more and more puzzles, it also solves a lot. Another new observations with the James Webb Space Telescope has just revealed collection of ancient galaxies that packed a massive punch, shaping the entire universe when it was less than 1 billion years old. The international team found the galaxies, which resemble dwarf galaxies that exist today, played a vital role during a crucial stage of cosmic evolution that occurred between 500 and 900 million years after the Big Bang. These small galaxies also vastly outnumbered larger galaxies in the infant universe, the scientists say, adding that it's likely the realms supplied most of the energy needed for a process called cosmic reionization. Cosmic reionization was critical to the growth and progression of the universe. As Hakim Atek, research lead author and an astronomer at the Institut d'Astrophysique de Paris, said, "We're really talking about the global transformation of the entire universe. The main surprise is that these small, faint galaxies had so much power, their cumulative radiation could transform the entire universe." Prior to around 380 million years after the Big Bang happened, during a period called the Epoch of Recombination, the now 13.8 billion-year-old universe had been opaque and dark. This was because, in its dense and ultra-hot state, free electrons endlessly bounced around particles of light, called photons. However, later, during the Epoch of Recombination, the universe had expanded and cooled enough to allow electrons to bond with protons and create the first atoms of hydrogen, the lightest and simplest element in the cosmos. This disappearance of free electrons meant photons were suddenly free to travel, and as a result, the dark age of the universe ended. The cosmos suddenly became transparent to light. This first light can be seen today in the form of a cosmic fossil that uniformly fills the universe called the cosmic microwave background, or CMB. Because electrons and protons have equal but opposite electric charges, these first atoms were electrically neutral, but they would soon undergo yet another transformation. After 400 million years, the first stars and galaxies formed. Then, during the era of reionization, neutral hydrogen, the predominant element in the universe, was transformed into charged particles. These particles are called ions. Ionization is caused by electrons absorbing photons and increasing their energy, breaking free from atoms. Until now, scientists weren't sure where this ionizing radiation came from. Suspects for the radiation source behind reionization had included supermassive black holes feeding on gas from accretion disks surrounding them, causing these regions to eject high-energy radiation, large galaxies with masses in excess of 1 billion suns, and smaller galaxies with masses less than this. But identifying smaller dwarf galaxies as main sources of this ionizing radiation was a challenge for a long time because of how faint they are. Luckily, the Webb telescope has spectroscopic capabilities in the infrared, and in fact, one of the reasons we built the observation is to understand what happened during the epoch of reionization. But noting that even with the impressive infrared observing power of James Webb, spotting these dwarf galaxies wouldn't have been possible without the help of Albert Einstein. More specifically, without the help of his 1915 theory of general relativity and an effect on light it predicts. General relativity suggests all objects of mass warp the very fabric of space and time, which are, in truth, united as a single entity called space-time. Our perception of gravity, the theory says, arises as a result of that curvature. The greater the mass of an object, the more extreme the curvature of space-time is. Thus, the stronger its gravitational effects are. Not only does this curvature tell planets how to move in orbits around stars, and in turn, tell those stellar bodies how to orbit the supermassive black holes at the centers of their home galaxies, but it also changes paths of light coming from the stars. Light from a background source can take different paths around a foreground object as it travels toward Earth, and the closer that path is to an object of great mass, the more it gets bent. Thus, light from the same object can arrive to Earth at different times as a result of the foreground, or lensing, object. This lensing can shift the location of the background object in the sky, or it can cause the background object to appear in multiple places in the same image of the sky. Other times, light from the background object is amplified, and thus that object is magnified in the sky. This effect is known as gravitational lensing, and James Webb has been using it to great effect to observe ancient galaxies near the dawn of time, which it would otherwise have had no chance of seeing. To observe the newly studied distant and early dwarf galaxies and analyze the light they emit, James Webb used a galaxy cluster called Abell 2744 as a gravitational lens. With the mystery of reionization potentially solved, the team now aims to extend this study to a larger scale with another Webb's project called Glimpse. The researchers will first try to confirm that the particular location studied in this research is representative of the average distribution of galaxies in the universe. Then, beyond studying the reionization process, ATEC and colleagues will aim to better understand the formation of the very first galaxies, which, over the course of 12 billion years, grew into present-day galaxies, evidence for the first generation of stars. A piece of good news, evidence for the first generation of stars to exist in the universe has come to light thanks to observations made by James Webb. The proof is located in one of the most distant galaxies known. The galaxy, designated GNZ11, was discovered by the Hubble Space Telescope in 2015, and prior to the launch of the James Webb Space Telescope, it was considered the most faraway galaxy known. With a redshift of 10.6, it makes more sense to talk about how long ago it existed, rather than how far away it is. That's because we see GNZ11 as it was just 430 million years after the Big Bang due to the time it took for its light to travel to our corner of the cosmos. For comparison, the universe today is 13.8 billion years old. As such, GNZ11 was a prime target for James Webb to study. Now, 2 new papers describe profound discoveries about GNZ11 that reveal vital details about how galaxies that existed in the early universe were able to grow. GNZ11 is the most luminous galaxy known at this particular redshift, and indeed, this has become a common theme for high redshift galaxies, now almost regularly being found in the early universe by James Webb. Many of them appear much brighter than what our models of galaxy formation predict they should be. Those predictions are based on the standard model of cosmology. Now, Webb's new observations seem to have shed light on what is going on. An astronomy team, led by Roberto Maiolino of the University of Cambridge, has probed GNZ11 with Webb's 2 near-infrared instruments, the NIR-CAM and the NIR-SPEC. The researchers discovered evidence for the first generation of stars, called population 3 stars, as well as for a supermassive black hole gobbling up huge amounts of matter and growing at a vastly accelerated rate. Scientists can calculate the age of a star based on its abundance of heavy elements, which would have been formed by previous generations of stars that lived and died, spewing those heavy elements into space where they ultimately get recycled in star-forming regions to form new stellar bodies. The youngest stars that have formed during the past 5 or 6 billion years are referred to as population 1 stars and have the highest abundance of heavy elements. Our Sun is a population 1 star. Older stars contain fewer heavy elements because there had been fewer generations of stars before them. Older stars contain fewer heavy elements because there had been fewer generations of stars before them. We call these population 2 stars, and they live in the oldest regions of our Milky Way galaxy. However, population 3 stars have been purely hypothetical up until now. These would have been the first stars to form, and because no other stars came before them, they would have contained no heavy elements and be made from only the pristine hydrogen and helium forged during the Big Bang. These first stars are also thought to have been extremely luminous, with masses equal to at least several hundred suns. Although astronomers still haven't seen population 3 stars directly, Maiolino's team detected indirect evidence for them in GNZ11. NIR-SPEC observed a clump of ionized helium near the edge of GNZ11. This helium gas is being ionized by something that's producing huge amounts of ultraviolet light, with that something inferred as the population 3 stars. Potentially, the helium witnessed is leftover material from those stars' formation. The amount of ultraviolet light required to ionize all that gas requires about 600,000 solar masses of stars in total, shining with a combined luminosity 20 trillion times brighter than our Sun. These figures suggest distant galaxies, such as GNZ11, would have been more adept at forming massive stars than galaxies in the modern universe. Meanwhile, according to a second set of results, Maiolino's team also found evidence for a 2 million solar mass black hole at the heart of GNZ11. Specifically, they found extremely dense gas that is common in the vicinity of supermassive black holes accreting gas. These were the first clear signatures that GNZ11 is hosting a black hole that is gobbling matter. The team also detected a powerful sleet of radiation flowing off the accretion disk of matter swirling around the black hole, as well as ionized chemical elements typically found near accreting black holes. It is the most distant supermassive black hole discovered so far, the team says, and its gluttonous appetite leads to its accretion disk becoming dense and hot and shining brightly. This, combined with the population 3 stars, is what makes GNZ11 shine so brightly, the researchers believe, without breaking standard cosmology as some have prematurely claimed. An extremely red, supermassive black hole growing in the early universe. Elsewhere, using the James Webb Space Telescope, astronomers have discovered an extremely red supermassive black hole growing in the shadowy early universe. The red hue of the supermassive black hole, seen as it was around 700 million years after the Big Bang, is the result of the expanding universe. As the universe balloons outward in all directions, light traveling toward us gets redshifted, and the redshifted light, in this case, indicates a cloak of thick gas and dust shrouding the black hole. Examining Webb's data, the astronomy team led by Lucas Furtak and Adi Zitrin of the Ben-Gurion University of the Negev was also able to determine the mass of the supermassive black hole. At around 40 million times the mass of the Sun, it is unexpectedly massive in comparison to the galaxy in which it resides. The team also found that the supermassive black hole, which is located around 12.9 billion light-years away from Earth, is rapidly feasting on the gas and dust around it. In other words, it's growing. As Furtak said in a statement, 3 very compact yet red-blooming objects prominently stood out and caught our eyes. Their red dot appearance immediately led us to suspect that it was a quasar-like object. Quasars are created when copious amounts of matter surround supermassive black holes like this one. This matter forms a disk of gas and dust called an accretion disk that gradually feeds the black hole. The immense gravitational influence of the black hole churns this matter, generating intense temperatures and causing it to glow. Additionally, matter that doesn't fall into the supermassive black hole is channeled to the cosmic titan's poles. Particles in these regions are accelerated to speeds approaching that of light as highly collimated jets. As these relativistic jets are blasted out, the eruptions are accompanied by bright electromagnetic emissions. As a result of these phenomena, quasars powered by supermassive black holes in active galactic nuclei are often so bright that the light they emit often outshines the combined light of every star in the galaxy that surrounds them. The vast amount of radiation being emitted from around this particular supermassive black hole caused it to take on a small, point-like appearance in Webb's data. Analysis of the object's colors indicated that it was not a typical star-forming galaxy. This further supported the supermassive black hole hypothesis. Together with its compact size, it became evident this was likely a supermassive black hole, although it was still different from other quasars found at those early times. But noting that the early quasar wouldn't have been visible even to the powerful infrared eye of James Webb without a little help from an effect predicted by Albert Einstein in 1915. In this case, the Webb telescope used a galaxy cluster called Abell 2744 as a foreground lensing body to amplify light from background galaxies, which are otherwise too distant to see. This revealed the extremely red quasar they zeroed in on, originally in the form of 3 red dots. Further analysis of the background source revealed its light must have come from a compact region. According to team member and Princeton University researcher Jenny Green, all the light of that galaxy must fit within a tiny region the size of a present-day star cluster. The gravitational lensing magnification of the source gave us exquisite limits on the size. Even packing all the possible stars into such a small region, the black hole ends up being at least 1% of the total mass of the system. The discovery further adds to the mystery of how supermassive black holes, which can be millions or even billions of times as massive as the Sun, grew to such huge sizes during the universe's infancy. And as told, James Webb has detected a wealth of little red dots over time. These could also indicate feeding supermassive black hole-powered quasars in the early universe, maybe meaning a striking black hole growth conundrum could soon be solved. In a way, it's the astrophysical equivalent of the chicken and egg problem. We do not currently know which came first, the galaxy or black hole, how massive the first black holes were, and how they grew. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.